Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today, we're diving deep into Azure Gateway Load Balancer, or GWLB for short. This is a game-changing service that Microsoft introduced to solve a critical challenge in cloud networking. How do you transparently insert network virtual appliances into your traffic flow without creating complex routing nightmares? Let me paint you a picture. Imagine you're running a large enterprise application in Azure. You need to inspect all traffic with a firewall, maybe run some intrusion detection, and perhaps do some traffic shaping. Traditionally, you'd have to route all your traffic through these appliances, creating potential bottlenecks and single points of failure. That's where Gateway Load Balancer comes in. Gateway Load Balancer is a fully managed, highly available service that operates at Layer 3 of the OSI model. It is designed to enable transparent insertion of network virtual appliances, or NVAs, into your network traffic path. What makes it special is that it maintains the original source and destination IP addresses while distributing traffic across multiple NVA instances. Think of it as an invisible traffic director that sits in your network path, seamlessly steering packets through your security appliances without your applications even knowing they're there. It's like having a transparent security checkpoint that doesn't slow down or complicate your traffic flow. In this presentation, we will explore everything from the basic concepts to advanced deployment scenarios. I will show you real commands, share practical examples, and help you understand when and how to use this powerful service. Whether you are a network engineer, security professional, or cloud architect, this knowledge will be invaluable for designing robust, scalable network architectures in Azure. How Gateway Load Balancer works. Let me explain how Gateway Load Balancer actually works under the hood. This is where things get really interesting from a networking perspective. Gateway Load Balancer uses a technology called VXLAN encapsulation. Now, if you are not familiar with VXLAN, it stands for Virtual Extensible LAN, and it is a network virtualization technology that encapsulates Layer 2 Ethernet frames within Layer 4 UDP packets. This allows the GWLB to preserve the original packet information while routing it through your network virtual appliances. Here is the flow. When traffic hits your standard load balancer or public IP that is chained to a gateway load balancer, the GWLB intercepts that traffic. It then encapsulates the original packets using VXLAN, adding a special header that preserves all the original packet information. This encapsulated traffic is then sent to one of your healthy NVA instances. The beauty of this approach is that your NVAs receive the complete, original packet. They can inspect it, modify it if needed, apply security policies, log it, whatever you need. Once the NVA is done processing, it sends the packet back to the GWLB, which removes the VXLAN encapsulation and forwards the traffic to its original destination. This diagram I'm showing illustrates the complete traffic flow. Notice how the GWLB acts as a transparent bump in the wire. Your applications don't need any special configuration. They just send and receive traffic normally. The GWLB and NVAs handle all the complexity behind the scenes. One crucial point. The GWLB maintains session affinity using a 5-tuple hash. This means that all packets from a specific flow, same source IP, source port, destination IP, destination port, and protocol, will always go to the same NVA instance. This is critical for stateful inspection and ensures that your NVAs can properly track connections. The health probing mechanism is also sophisticated. GWLB continuously monitors your NVA instances and automatically removes unhealthy instances from the pool. This happens within seconds, ensuring minimal disruption to your traffic flow. Key features and capabilities. Now let's dive into the key features that make Gateway Load Balancer such a powerful tool in your Azure networking arsenal. Each of these features addresses specific challenges that network and security teams face when deploying NBAs at scale. First up is transparent network traffic inspection. This is the crown jewel of GWLB. Your NBAs can inspect all traffic, both inbound and outbound, without requiring any changes to your application architecture. The transparency is complete. Applications see the original source and destination IPs, ports remain unchanged, and all protocol information is preserved. This is crucial for security appliances that need to make decisions based on the actual traffic characteristics. High availability and scalability are built into the DNA of GWLB. You can deploy multiple NBA instances behind a single GWLB, and it automatically distributes traffic among them. If one NBA fails, traffic is seamlessly redirected to healthy instances. You can scale to handle massive flows per second. That's throughput that can handle even the largest enterprise workloads. The service chaining capability is what I find most elegant. You can chain a gateway load balancer to any standard SKU public IP or standard load balancer. This means you can insert security inspection into existing architectures without redesigning your entire network. Just chain the GWLB, and suddenly all your traffic is being inspected. Support for multiple NVIDIA vendors is another key strength. Whether you're using Palo Alto Networks, Checkpoint, Fortinet, F5, or any other major vendor, they all have NBAs that work with GWLB. Microsoft has worked closely with these vendors to ensure compatibility and optimal performance. The health probe mechanism deserves special mention. It supports both TCP and HTTP/HTTPS probes, allowing you to verify not just that your NBA is running, but that it's actually capable of processing traffic. You can configure probe intervals, timeout values, and unhealthy thresholds to match your specific requirements. Cross-subscription support opens up interesting architectural possibilities. You can have your NBAs in a centralized security subscription and chain GWLBs from multiple application subscriptions. This supports hub and spoke architectures and helps maintain separation of duties between security and application teams. Creating a gateway load balancer. Alright, let's get our hands dirty and actually create a gateway load balancer. I'll walk you through the process using Azure CLI commands, explaining each parameter so you understand exactly what we're doing. First, we need to create the gateway load balancer itself. The command starts with a znetwork lb create. The name parameter gives our load balancer a name. I am using my gateway lb here, but you should use something descriptive for your environment. The resource group parameter specifies where to create it. Make sure this resource group already exists, or create it first. The critical parameter here is SKU, which must be set to gateway. This tells Azure we want a gateway load balancer, not a standard or basic load balancer. The VNet name and subnet parameters specify where to place the load balancer. This subnet will host the front-end IP configuration of your GWLB. Next, we create the backend pool. This is where we will add our NBA instances. The command aznetwork lb address pool creates an empty pool. We will populate it later when we have our NBAs deployed. The lb name parameter must match the name of the GWLB we just created. The health probe configuration is crucial for high availability. The command shows creating an HTTP probe on port 65500. This port is special. It's the recommended health probe port for GWLB scenarios. Your NBAs should be configured to respond to health checks on this port. The interval parameter sets how often to probe, 5 seconds, and the threshold sets how many failed probes before marking an instance unhealthy. Creating the load balancing rule ties everything together. This rule uses protocol all, which means it will forward all traffic regardless of protocol. The front-end port and back-end port are both set to 0, which in GWLB context means all ports. This ensures that whatever traffic comes in gets forwarded to your NBAs exactly as received. The front-end IP name references the front-end IP configuration that was automatically created when we made the GWLB. The backend pool name and probe name reference the resources we created in the previous steps. One important note: these commands create the GWLB infrastructure, but you still need to deploy your NBAs and add them to the backend pool. That's what we will cover in the next section. Configuring network virtual appliances. Now that we have our gateway load balancer created, let's talk about configuring the network virtual appliances that will actually process your traffic. This is where the rubber meets the road, and proper configuration here is critical for a successful deployment. First, let's deploy an NBA. I am showing an example using a marketplace image, but in reality, you would use an image from your preferred vendor, Palo Alto, Checkpoint, Fortinet, and so on. The key parameters here are the size, which should be appropriate for your expected traffic load. I am using standard D4SV3 as a starting point, but you might need larger instances for high throughput scenarios. The public IP address parameter is set to an empty string because NBAs behind a GWLB typically don't need public IPs. They are receiving encapsulated traffic from the GWLB, not direct internet traffic. The VNet name and subnet should place the NBA in a subnet that can communicate with your GWLB. Now, here's a critical configuration step that's often missed: enabling IP forwarding. The command AZ network NIC update with IP forwarding true is absolutely essential. Without this, your NBA won't be able to forward packets that aren't destined for its own IP address. Since the NBA is inspecting traffic between other sources and destinations, IP forwarding must be enabled. Adding the NBA to the backend pool is straightforward with the AZ network LB address pool address add command. You are essentially telling the GWLB, here is an NBA instance that can process traffic. The IP address parameter should be the private IP of your NBA. Inside the NBA itself, you need to configure it to handle VXLAN encapsulated traffic. This typically involves setting up a VXLAN interface that listens on UDP port 10800, the standard GWLB port, and configuring your security policies to process the decapsulated traffic. Each vendor has specific guides for this. I strongly recommend following your vendor's GWLB integration documentation. Don't forget about the health endpoint. Your NBA must respond to health probes on the port you configured in our example. This could be as simple as a web service that returns 200 OK, or as complex as a health check that verifies all security services are operational. For production deployments, you will want multiple NBAs for high availability. Simply repeat the deployment process and add each instance to the backend pool. The GWLB will automatically distribute traffic among all healthy instances. Chaining GWLB to resources. Service chaining is where Gateway Load Balancer really shines. This is the process of connecting your GWLB to your actual workload resources, your standard load balancers and public IPs. Let me show you exactly how this works and why it's so powerful. The first example shows chaining to a standard load balancer. The command uses a Z-Network LB frontend IP update to modify an existing frontend IP configuration. The magic parameter here is Gateway LB. You provide the full resource ID of your gateway load balancer's front-end IP configuration. This creates the chain. Now all traffic flowing through this standard load balancer will be transparently redirected through your GWLB and NBAs first. The benefit of this is that your applications behind the standard load balancer do not need any changes. They continue to receive traffic normally, but now it has been inspected and processed by your security appliances. The return traffic follows the same path in reverse, maintaining complete symmetry. Chaining to a standalone public IP follows a similar pattern. The AZ network public IP update command with the gateway LB parameter creates the chain. This is perfect for scenarios where you have virtual machines with public IPs that need security inspection. Maybe it's a jump box, a web server, or any other resource with direct internet exposure. For cross-subscription scenarios, the process is the same, but you need to ensure proper permissions. The identity performing the chaining must have at least network contributor rights on both the chained resource and the gateway load balancer. The resource ID format I'm showing includes the full path with subscription ID, making cross-subscription references explicit. Here's an important consideration. You can chain multiple standard load balancers and public IPs to the same gateway load balancer. This creates a hub-and-spoke security architecture where all your internet-facing resources are protected by a central set of NBAs. It's incredibly powerful for maintaining consistent security policies. The traffic flow after chaining is important to understand. Inbound traffic hits your public IP or load balancer, gets redirected to the GWLB, flows through an NBA for inspection, returns to the GWLB, and finally reaches your application. The entire process typically adds just 1 to 2 milliseconds of latency, negligible for most applications. One tip: always verify your chaining configuration using a Z Network LB frontend IP show or a Z Network public IP show. The output will include the gateway LB property if chaining is configured correctly. Common architecture patterns. Let's explore the most common architecture patterns for gateway load balancer. These patterns have emerged from real-world deployments and represent best practices for different scenarios. Understanding these will help you design the right solution for your specific needs. The centralized security pattern is probably the most popular. In this architecture, you deploy all your NBAs in a dedicated security virtual network or subscription. Your gateway load balancer lives here too. Then, you chain resources from multiple application virtual networks to this central GWLB. This creates a hub-and-spoke security model where all internet traffic flows through your centralized security stack. It is perfect for organizations that want consistent security policies and centralized management. The main advantages here are simplified management. Your security team owns and operates the NBAs independently of application teams. You get consistent policy enforcement across all applications, and you can scale your security infrastructure independently of your applications. The potential drawback is that all traffic must traverse to the central location, which could add latency for geographically distributed applications. The distributed security pattern takes a different approach. Here, each application or business unit has its own gateway load balancer and set of NBAs. This provides complete isolation between different applications or tenants. It's ideal for multi-tenant scenarios or when different applications have vastly different security requirements. This pattern gives you maximum flexibility. Each application can choose its own NB of vendor and security policies. Performance is optimized since traffic doesn't need to traverse to a central location. The trade-off is increased management overhead and potentially higher costs due to resource duplication. The hybrid model combines elements of both. You might have a central GWLB for common security functions like DDoS protection and basic firewall rules, with additional distributed GWLBs for application-specific security needs. This balances the benefits of centralization with the flexibility of distribution. The diagram shows how these patterns differ in practice. Notice how the centralized model creates a clear security perimeter, while the distributed model embeds security within each application boundary. The hybrid model layers security functions, with some centralized and others distributed. When choosing a pattern, consider your organizational structure, compliance requirements, performance needs, and operational capabilities. There is no one-size-fits-all answer. The best pattern is the one that aligns with your specific requirements and constraints. High availability and scaling. High availability and scaling are critical aspects of any production gateway load balancer deployment. Let me share the key considerations and best practices that will ensure your security infrastructure can handle failures gracefully and scale with your growing needs. First, let's talk about availability zones. Gateway Load Balancer is a zone-redundant service by default in regions that support availability zones. This means Microsoft handles the zone redundancy for the GWLB itself. You don't need to do anything special. However, your NBAs are a different story. You should deploy NBA instances across multiple availability zones to ensure your security inspection remains available even if an entire zone fails. The scaling model for GWLB is elegant. The Gateway Load Balancer itself scales automatically. You do not need to worry about its capacity. It can handle up to 10 million flows per second without any configuration on your part. The scaling bottleneck, if any, will be your NBAs. That is why choosing the right NBA size and count is crucial. For NBA scaling, you have two dimensions: scale up and scale out. Scaling up means using larger virtual machine sizes for your NBAs. If you are hitting CPU or memory limits, moving from AD4-SV3 to AD8-SV3 might solve your problems. Scaling out means adding more NBA instances to your backend pool. The GWLB will automatically distribute traffic among all healthy instances. Auto-scaling is possible but requires careful planning. You can use virtual machine scale sets with your NBA images and configure auto-scaling rules based on metrics like CPU utilization or throughput. However, remember that NBAs often need time to initialize and load security policies. Set your scale-out thresholds conservatively to avoid constant scaling actions. Health monitoring goes beyond basic probes. While the GWLB Health Probe ensures basic connectivity, you should implement comprehensive monitoring of your NBAs. Use Azure Monitor to track metrics like throughput, connection count, and resource utilization. Set up alerts for anomalies that might indicate problems before they impact availability. The failure scenarios table I'm showing lists common failure modes and how GWLB handles them. Single NVIA failure. Traffic redirects to healthy instances within seconds. Availability zone failure. If you have distributed NBAs across zones, traffic continues flowing through NBAs in healthy zones. GWLB itself fails. Extremely rare due to zone redundancy, but if it happens, traffic bypasses inspection and flows directly, fail open behavior. One critical tip: always test your high availability setup. Simulate failures by stopping NBA instances and verify that traffic continues to flow. Check that your monitoring alerts fire correctly. Measure the failover time to set appropriate expectations. Remember, high availability isn't just about the technology. It's about proving that your design works under failure conditions. Monitoring and troubleshooting. Effective monitoring and troubleshooting are essential for maintaining a healthy gateway load balancer deployment. Let me walk you through the key metrics to watch, common issues you might encounter, and the tools and techniques for resolving them quickly. Starting with monitoring, Azure provides several metrics specifically for Gateway Load Balancer. The processed bytes metric shows the total traffic volume flown through your GWLB. This helps you understand usage patterns and plan capacity. The processed flows metric counts the number of network flows, which is useful for understanding connection patterns and detecting anomalies. Health Probe Status is your early warning system. This metric shows the percentage of successful health probes to your NBAs. If this drops below 100%, you know some NBAs are unhealthy. Set up alerts when this metric falls below your desired threshold. For example, 80%, to give you time to respond before impact becomes severe. The commands I am showing demonstrate how to query these metrics using AZ. The AZ Monitor Metrics List command pulls specific metrics for time ranges. You can use this data to build dashboards or feed into your monitoring systems. Pay attention to the aggregation types. Some metrics make sense as averages, others as totals or maximums. For troubleshooting, Network Watcher is your best friend. The next hop feature helps verify that traffic is correctly routed through your GWLB. The IP Flow Verify tool confirms whether traffic is allowed or blocked. The Connection Troubleshoot feature tests end-to-end connectivity through the entire path, including your GWLB and NBAs. Common issues I've seen include asymmetric routing, where inbound and outbound traffic take different paths. This breaks stateful inspection in your NBAs. The solution is ensuring both directions of traffic flow through the same GWLB and NBA instance. Connection timeout issues often stem from misconfigured session persistence or NBAs dropping long-lived connections. Review your NBA timeout settings and ensure they align with your application needs. When packets seem to disappear, use packet capture on your NBAs. Capture on both the VXLAN interface, where encapsulated traffic arrives, and on the regular interfaces, where decapsulated traffic is processed. This helps identify whether the issue is with GWLB delivery or NBA processing. The diagnostic checklist I always follow. First, verify health probe status. Are all NBAs healthy? Second, check metrics for any anomalies in traffic patterns. Third, use Network Watcher to trace packet flow. Fourth, review NBA logs for processing errors. Fifth, check for any Azure service health issues in your region. This systematic approach usually identifies the root cause quickly. Cost optimization and best practices. Let's wrap up with cost optimization strategies and best practices for Gateway Load Balancer. Understanding the pricing model and following these recommendations will help you build a solution that is both effective and economical. Gateway Load Balancer pricing has three components. First, there's an hourly charge just for having the GWLB deployed. This is approximately $0.225 per hour in most regions. Second, you pay for processed data at roughly $0.005 per gigabyte. Third, you pay for your NVIDIA virtual machines at standard virtual machine rates. The GWLB costs are usually minimal compared to NVIDIA costs, so optimizing NVIDIA usage is where you'll find the biggest savings. For cost optimization, right-sizing your NVAs is crucial. Start with smaller instances and scale up only when you see performance constraints. Use Azure Advisor recommendations to identify overprovisioned virtual machines. Consider using spot instances for non-production environments. You can save up to 90% on virtual machine costs. The example calculation I'm showing demonstrates costs for a typical deployment. 3D4SV3 NVAs running 24 hours a day, 7 days a week, plus GWLB processing 10 terabytes monthly. The monthly cost comes to about $1,300, with virtual machines representing over 90% of that. This reinforces why virtual machine optimization is so important. Deployment best practices start with automation. Use infrastructure as code, either ARM templates, Bicep, or Terraform, to deploy your GWLB infrastructure. This ensures consistency and makes disaster recovery much easier. Always deploy NVAs across availability zones for redundancy. Use dedicated subnets for your NVAs to simplify network security group rules. Design principles I always follow. Keep it simple. Do not over-engineer your solution. Plan for growth. Ensure your architecture can scale without major redesign. Document everything. Your future self will thank you. Test failure scenarios. Do not wait for production issues to find out if your HA works. Monitor proactively. Set up alerts before you need them. Security considerations are paramount. Even though your NVAs provide security, they need protection too. Use network security groups to restrict management access to your NVAs. Enable Azure DDoS protection standard on the virtual network containing your GWLB. Use managed identities for your NVAs to access Azure resources securely. Regularly update your NVIDIA software to patch vulnerabilities. Performance optimization tips. Place your GWLB and NVAs in the same region as your workloads to minimize latency. Use accelerated networking on your NVIDIA virtual machines for better throughput. Configure your NVAs for optimal performance. This varies by vendor, but often involves tuning buffer sizes and connection limits. Monitor CPU and memory usage to identify bottlenecks before they impact service. Thank you for your attendance. Please consider subscribing to the channel.